So, all you have, what are the names of the groups?
Placebo, low A.
So placebo, okay, yeah, I remember low A, high A.
Low B and high B.
Right, so you have 5 groups, and this is 1241?
49.
49. And it refers back to 1239, right? And then you have the means. So you have the X bars from each group, and then you have the standard deviations from each group, right? So X bar sub I, okay? And then it asks you, I wanted you to completely build the ANCOVA table from this. So, and it's an extra. You can't use, Taylor emailed me, I can't get this to work right. And he was trying to run the ANCOVA, in Excel, you click on data, then you go to data analysis, and you pop up one-way ANCOVA, but it won't work because you don't have the raw data. You don't have the values that went into this mean for placebo and so on. All you have is the mean.
So you just want us to put everything in Excel, not actually use Excel.
Right. Well, you're going to use cell formulas that you make yourself. Right? So the first thing you need is the grand mean, which I label as X bar dot, right, in a one-way setting. So that's the grand mean. How do you get the grand mean?
It's a weighted mean.
It's a weighted mean of these, right? It's arithmetic, but it's complicated arithmetic. But to get the mean, all you need to know is, well, what was the sum in placebo? And that's the same as summing up all the placebo ones. And then what was the sum in low A? And this, so you get the sums, add them up, and then divide by the total n, right? So each of these will have an n on them also. So let me put a column for n. Right? So this is n1, n2, n3, and so on. Right? So the grand mean will be the sum of each ni times x bar I. Right? Summed across all I groups. Then divided by the sum of what? The ni's. Right? So that's your grand mean.
Double sum.
It's not a double sum, it's a sum over a sum.
Okay. I thought the NI was in the secondary sum.
No. This is not in that sum. Then a similar thing for your SP. How do you get SP squared?
Right.
It's a weighted mean of the S's, right? Now I can't remember, did they give you S squared or just S's?
S squared, S squared.
They're S squared. Okay, so it looks like that. So to get SP, it's a weighted mean of those, but you have to weight by what the divisor was when you compute variances. And what's the divisor when you compute variances? N minus 1, not n. When we do the weighted mean of the x bars, each is a sum divided by n, so you weight back by the n's. But these are sums of squares divided by n minus 1, so you need to weight back. So this is going to be the sum of ni minus 1 times si squared, and then divide by what? What'd you say, Todd?
Sum of the NI minus 1.
The sum of the ni's minus 1. Which, that you can get, if you think about what you're doing here, you've got I groups, there's 5 groups, so your capital I is a 5. So this sum is going to go 1 to 5. This is actually equal to the sum of the ni's minus 5. Right? Like that. That's an ugly 5, but that's a 5. Right? So, but it's easier if you just write it out like that. Right? So that's SP squared. And what is SP squared in an ANCOVA table?
MSE.
That's MSE. Right? So in your ANCOVA table, you've already got the mean squared error. If you got the mean squared error, then you can get the sum of squares by multiplying by the degrees of freedom for error, but you can figure out what that would be. Now, how do you get the sum of squares for model? Actually, let's get sum of squares total. That's easier. So sum of squares total. How do you get sum of squares total? Well, by definition, it's the sum of the squares xi minus x bar, right? I said that's easier, but it's actually not easier. We can't get it here because we don't have the individual xi's. But we can get sum of squares due to the model. And how do we get that? And in your homework document, I posted that little, I just scanned that out of your book, right? The little table. What's the formula it gives for sum of squares model? Does anybody have it open? Taylor?
So it is the sum of x bar I minus x bar. I'm
X
sorry,
bar I minus,
x bars, and then all of that squared, and you already put the I on from.
right,
And that is a double sum.
right? It actually, it would be a double sum, but since there is no j subscript, when you do this, the extra summation with the j, meaning the jth person in the ith group, then it's the same as multiplying by the sample size in that group. And so we made that into a single sum, right? So the ni's, you got all of those. The x bar i's, you got all of those. The grand mean we just computed. So you can get the sum of squares model. Now if you got the sum of squares for error and the sum of squares for the model, what's the sum of squares total? So this we can't do, so I put a question mark. But then it's equal to sum of squares model plus sum of squares error. That you'll have. So then once you have those three things, you can figure out the degrees of freedom for each line, which gives you the mean square for each line. Once you know the mean squares, you can get the F statistic and the p-value for the F statistic. How do you get p-value for your F statistic? Brant? FCDF on the calculator. He just asked that question right before class. That's why I picked on him.
So we don't actually need to do C and D from the book then, because you gave us different data.
Right, C and D, just read C to me. I can't remember what it says.
You gave the degrees of freedom for the F statistic.
Give the degrees of freedom for the F statistic. Yeah, you'll answer it from your ANCOVA table, right? So it's just, what are the degrees of freedom? Numerator is 4, 1 minus the number of groups. The denominator is whatever your error degrees of freedom turns out to be, which is your total n, sum of the ni's, minus 1 is your total degrees of freedom. So subtract your model degrees of freedom, and you got your error degrees of freedom. Right? So, and then what's D?
It says the F statistic is 2.64, find the associated p-value.
Yeah. So F is not equal to 2.64 now, because I changed the data. So put what it is equal to off of your ANCOVA table and compute the p-value. So you don't really have to do D. It'll already be done. That's part of your table. And then the whole thing Brent asked about to bring all this up was the contrast. So now how do we do contrast? Actually, I think I want to keep this little table. Can I erase all this? Is everybody done with this? Is there a way to copy and make a new page out of this page?
Yeah, you can clone it.
Can what?
Clone it.
Uh-oh, there's a word. How do you clone it?
I guess edit.
Yeah, it's gonna be up there somewhere.
Edit.
Copy.
No,
Or duplicate.
there's a legit clone button.
Yeah, we'll try copy. And then about paste.
There's also a duplicate.
Degrees of freedom.
That didn't work. Oh, it did work. Ha. Okay. I'm probably more excited about that than I ought to be. So let's erase all this. So now, Nate, you can. Nate's busy. So how do we do contrast? What's the first contrast you're supposed to do?
Oh, sorry.
Versus,
The average of the two lows.
So contrast C1, I'll call it. And it says average of
The two low dose treatments,
two lows, okay, versus
placebo.
placebo. Okay? So now I wrote right where I wanted to do stuff. But I'm going to make a column for the C, or not C, the AIs. And the AIs are the contrast coefficients. Remember that notation? So what would the AIs be for that contrast? Placebo is versus placebo, so it gets a 1. Or a negative 1. It doesn't matter which side you make positive, which you make negative. So I'll make it a 1. And then average of the two lows. Low A gets negative 0.5 or negative 1/2. And then low B, or what does high A get? 0. It's not involved in this contrast. And then a negative 0.5, and then another 0. So in Excel, when you have this table with these means, you can just make a column with your contrast coefficients, and then multiply, make another column that is a cell formula equal this cell times that cell, this cell times that cell, and so on, and then sum that column. And there's your contrast.
So you do the CI times the XI?
Right. The contrast, so C1 is equal to, C anything, is the sum I equal 1 to capital I of A sub I times X bar sub I. Right? So fancy notation with the summation, but it's just each of the contrast coefficients times its respective mean, sum them up.
And that's an AI, not a Q.
That's an AI, right? Okay? And then whatever the next contrast is, what is the next one?
Lower doses versus high doses.
The average of the two lows versus the two highs?
Yeah.
Okay. So what do lows be?
Well, positive 0.5. And the highs would be negative, or you can just make the highs positive 0.5.
Yeah, I'll actually, let me make a new column and I'll erase these words. So that contrast, placebo is not involved. So that gets a 0. And then the average of the two lows, positive 0.5. I can't write small enough with this fancy marker. I can do this? Is that what you were getting ready to tell me? I never saw that until right then. Negative, that must be the size it was on. 0.5, negative 0.5, and then positive 0.5, and positive 0.5. Check that they sum to 1 or sum to 0 to make it a contrast. They do. So then, got it? Yeah.
So the first one, you'd be summing up 3 different multiplications. The placebo, A of I times mean, low A,
Yep.
A of I times mean.
Yep. There'll be 3. Yeah.
Okay.
Technically you sum all 5 every time, but some of them have zeros,
Okay.
right? So here you're summing 3 things, here you're summing 4 things. If they say check placebo against the average of all the others, then it would be a 1, then what?
Negative 0.25.
Negative 0.25 all the way down. Everybody seen how this works? And then you'll need to compute the standard error of the contrast, and you got to do it by hand. But what is the formula? Standard error of CI is
C1 times, or the square root of something where.
not C1.
Square root of the AI squared over.
Okay, the square root of the sum of the AI squared over NI. And the over NI needs to be, I can't remember, is it AI over NI quantity squared?
No, just the.
Yeah, so just the tops, so it's like this.
No, it's just the top square.
Well, I meant for that to be there. Ah. So AI squared and then like that, right? And that's an NI. My handwriting's bad enough without this thing messing it up even more.
Just so you know, if you press little arrows, you can just undo what you lost did.
Those things?
Yep.
Hey, that's good to know. And then this isn't everything. I need that under square root. Then I need something else out front.
This is MSE,
Root MSE, which in the notation we were using,
is SE.
S sub t, which is root mean squared error. Right? So there's your contrast standard error. And now you can form a test statistic. Yeah, that's what they want, right? A test statistic and a p-value? Or do they want a confidence interval? Okay. So you're going to take CI, so your t test statistic is CI minus 0. So you don't need that, over the standard error of CI. And there's your t test statistic. You can get a p-value using your t CDF function and the error degrees of freedom. The degrees of freedom that go into that SP. Yep.
And you're summing up AI squared and then dividing by, or are you summing up AI squared divided by?
The sum is across the whole parenthesis.
Okay.
So you take AI, square it, divide by its respective NI, and then sum to the next one of those. Okay? And I think that gets you through all of that problem. And then I sent you SAS code to do the other part because this enterprise guide is broken. I don't know what happened and they don't know what happened and they haven't got it fixed yet. So we're just using regular SAS and I sent you code and all you got to do is figure out, okay, I need to change this variable name to this and this variable name to that and run it. It should just give you everything you need. The main thing is, can you read SAS output, not can you program in SAS. Okay. So then today we're going to do ANCOVA. Instead of ANOVA, it's ANCOVA. Analysis of covariance. This is not in your textbook, so this is a supplemental section. So the first thing we need to define is the word covariance. Right? So think of it as you have a dependent variable y, and it has variability. It has variance. But now if I got another variable that's related to y, say x, then it co-varies with y. So think of height and shoe size. We talked about that when we were doing regression, right? So height and shoe size are correlated, so they co-vary. Right? And so analysis of covariance adjusts group differences for continuous X variables adjust group differences for continuous X variables. All right, so it'd be like well, a common thing in the pharmaceutical world that I deal with is adjusting for body weight. All right, so when you're trying to figure out what's the best dose of this drug to use, right? So you have maybe 4 dose groups: low, medium, high, and placebo. So that's a 0. Right? So I got 4 dose groups. Which one is the best dose to use? And if the clinicians say, well, it depends on how heavy they are. Right? If they weigh, you know, if they're overweight, they may need a higher dose. So you adjust for body weight. So it's a way of mathematically saying, okay, let's compute what they would need if everybody weighed exactly the same. So it moves the group means according to how much is the group mean weight different. Right? So well, I was going to draw a picture, but actually there's already a picture drawn. I will post, I haven't done it yet, but I will post this document out there for you to read. This is in place of a chapter in your book. This is a PDF file that I downloaded off the web. Right? I'm not going to talk about everything in here. It's actually from a course numbered 512, and if you see a 500 in front of a course number, what does that tell you? It's a master's levels class. So this is graduate level statistics, but the first part of this is very readable for undergrads. So I'm not, you guys are really smart undergrads, so I'm not worried about you at all. Okay, so analysis of covariance. And we'll start with one-way analysis of covariance, but analysis of covariance can apply to any ANCOVA model. One-way, two-way, three-way, 14-way. The whole idea is it's called covariance if you throw in a continuous variable x that's not a grouping variable or a classification variable. It's a continuous numeric variable. Right? So there. I want to get to a particular example. Yeah, this is the one I want. So this is fictitious data, small sample size, patients who have an aggressive form of cancer, and we want to know how long they live after they get diagnosed with this cancer, or after I start treatment on them. So this is a type of survival analysis, right? So down here in tiny little symbols is TRT, short for treatment. So this is treatment 1, treatment 2, treatment 3. So it's not a numeric variable, it's a categorical variable. Just this is the first treatment, second treatment, third treatment that they get randomized to. All right? So which treatment would you prefer to be on?
I assume the higher it is, the longer you live?
Yeah, this is longer you live, right? So you want to be on treatment 1, right? But wait, there's more to the story. If you analyze the data just as a one-way ANCOVA, here's the means from those groups that we saw. The first treatment, A, was 39.3 months of life. The next one was 24.6. The next one was 12. So basically 3 years, 2 years, and 1 year survival time, average survival time, right? So this is a one-way ANCOVA with no adjustment. But now, if you change your x-axis to represent the stage to which the cancer has progressed, so you've heard of stage 1, stage 2 cancers. So the stage of cancer they were in, what do you notice about the 3 treatments? Now treatment comes into it by the symbol they plot with. So a 1 means they were in group 1, a 2 means they were in group 2, and a 3 means they were in group 3. What do you notice?
Stage 3 cancer, you're not as long as it's in stage 1.
This is a horribly designed study, so they should fire their statistician. But in this study, all of the group 3 patients were end-stage cancer. All of the group 1s were early-stage cancer, and the 2s were the middle. So obviously this is made-up data to make a point stronger than it would ever be in real life. But this sort of thing does happen in real life, where the 1s tend to be at that end more than the 3s, and the 3s tend to be at this end more. Right? So it tells me, hey, I need to adjust for how far along they were when they start treatment. Right? So ideally, we build it into the design of the study. You would do what's called blocking. You would block, you would measure their stage disease, and then you would say, okay, let's take the 3 patients that were at end stage and randomize one of them to be a 1, one of them to be a 2, and one of them to be a 3. And then do the same thing, right? So ideally. But you can see this. This is going to mess me up probably, but you can see that there's this linear relationship across there. Right? So the idea of adjustment for stage, if I take the group mean for the 3s, it would probably be about that high. Right? So they were at 12 months. And then the mean of the 2s, I covered up one of the 2s. Oh, it's right there. So that's a 2 right there. The mean of the 2s is about right there. So the 1s there. And then the mean of the 1s is about right there. Right? So there's a big difference in those means. But now what the adjustment does is it fits this regression line. So it fits a regression line of the dependent variable y onto the covariate x. And then it says, okay, this mean is way different than this mean in terms of stage cancer. So think of dropping verticals. Here is x bar 1, here is x bar 2, and x bar 3. I want to then slide these points along the regression line until they're all at the same place in x. And the usual place to do that is the mean of all the x's. So ignore group. What's the overall average? It's probably right around in there. So that'd be your grand mean x bar dot. So this point slides up until it hits this vertical line. So it would be right there. This one's going to slide down till it hits that line, and this one's going to slide down till it hits that line. And the way I drew the picture, or the way they have it set up, they get awful close together when you all slide in there. So, I can't see. I gotta turn that off, right? Okay, so now after you adjust, here's your ANCOVA table. So you see a line in there for the x variable with 1 degree of freedom. Remember in regression, how many degrees of freedom does each x variable get? 1, right? So you get 1 degree of freedom for your covariate, and then you get I minus 1 for your classification variable, your class variable. So class variables treatment, it had 3 levels, so you get 2 degrees of freedom. Right? We had 9 total points, so 8 total degrees of freedom, and 1 plus 2 is 3, leaving 5 for error. Right? Now, how do I read the p-values here? Well, look at the covariate. Highly significant p-value. What is that telling me? First of all, what's it testing? What's the null hypothesis?
It's testing if it's known for covariance.
Okay, that's right. you could have used the word correlation, that's fine. There is no correlation between the X variable and the Y variable. That stage cancer does not predict how long you're going to live. And we know that's not right. We reject that hypothesis. Right? So stage of cancer does very significantly help predict how long you're going to live when you get diagnosed. Now look at the next p-value, 0.2478. What is that testing? That's a classification variable, so it isn't, oh, I forgot to say, you can use the word correlation or you can use the word slope. Is the slope of that line 0? If it's 0, then it's not helping predict. But now, for this one, we're not testing a slope equals 0. Now we're in an ANCOVA setting. So what analysis of covariance does is it combines regression with analysis of variance. So what's the null hypothesis for this F test? The treatments don't differ. The mean life expectancy in group 1 is the same as it is in group 2, is the same as it is in group 3. What's our conclusion? Don't reject that. So after we adjust for stage cancer, there doesn't seem to be any difference between these treatments. And when I was drawing lines, you saw that was happening. The 3 came up to the middle, the 2 was already in the middle, and the 1 came right down to it. And they were all real close together. So no real difference. Now, it doesn't always work that way, that the treatment effect goes away. Sometimes the treatment effect appears after you adjust. It's not there until you adjust. Right? So what you have to think of is, well, let's go back to the ANCOVA table. Yeah, right here. Go back to the ANCOVA table. If I take this covariate out of the model, where do its sum of squares go?
Goes into the air.
Goes into the air. The total sum of squares is the total amount, right? And then it's partitioned into these pieces. So if I don't explain some of the variability with X, then everything X can explain gets left unexplained, and it drops into the air term. So this 1297 drops in here to the air, and it makes the air sum of squares huge, which makes the mean squared error huge, which makes the bottom of the F statistic huge, which you lose power. Right? So whenever you can pull something out of the error term and explain it, you've increased the power of the test to detect differences. So oftentimes researchers will say, well, I have an imbalance among my treatment groups, so I need to adjust for that variable. Right? And this example was an overblown example of, yeah, huge imbalance. You had all the 8s down here in the 3s and all the 1s up here in group 1. But even if they're evenly distributed and there is no imbalance, you still should adjust for the covariate if it's a strong predictor, because it's pulling noise out of the air and explaining it. So then you gain power to detect differences between your groups. Okay.
Now, can you do, like, I know this is just one way, but as you go up, can you still have multiple, I don't know what call them, interaction terms like that? And with
Yes, you sure can.
Okay.
And this document goes into that. I'm not going to take class time to explain, but what you're talking about is, can I let the slopes be different, right, between the groups? An interaction term, remember, in regression setting, did we do interaction and regression? I'm not sure this book does that, because it only touches the tip of the iceberg on each type of analysis. But if you have different slopes, that's interaction. So you can take an interaction between your covariate and grouping variable and let the slope be different for the 3 groups. But if you do, then your comparisons don't make sense. So that's one of the assumptions they say should be met for analysis of covariance to be valid. Or not so much that the analysis is valid, but the comparison of the group means to be valid. Remember, you're sliding to the overall average mean. Well, if your slopes are different on the lines you're sliding along, then you make more of an adjustment to one group than another, and it depends on, well, where are you comparing at? If I compare it the overall mean, then I get one set of differences, but if I compare it some other number, the slopes are different, so they get closer together or further apart. It doesn't make sense. So here's the same scenario, but in this case, notice that the ones, I think, yeah, it's still early stage disease. So the ones have early stage, 2's middle, and 3 late stages. But now you can't draw a separate line, or draw a single line that hits all of the 1's, 2's, and 3's, right? So you fit a line, you fit your x variable without controlling for what group they're in. And so the ones would go like, what am I going to do? This thing, and
Have to click on your mouse button again up there,
mouse button.
and we can scroll down.
Oh, and I have to do that, right? I lost where I am. There. Now you get a line to that group, a line for that group, and a line for that group. And now if you slide the 3's along this line to the overall x, it's way up here. The 2's are about where they're at. The 1's would be way down here. And you can get a really dramatic difference, whereas right now, if you take the mean of this group, the mean of that group, and the mean of the 1's, they're all at about the same level, right? So the slope of the line is determined, and then it's applied to the 1's, the 2's, and the 3's. It's the same slope, but the intercepts are different, right? So the group means determine that intercept. So adjusting can separate points, or it can bring them together. So you never know before you do the analysis of which it's going to be. The main point is that if you have a covariate, that is an important predictor of your dependent variable. You should be adjusting for it. Even if you're balanced, even if the 2's were all spread around, the 3's were all spread around, you still should adjust for it because it will decrease your error.
So in the first study, you were able to draw one line. When you actually run this,
Yeah.
does it figure out if it can do that? Or
No, it actually should have been 3 separate lines. But let me go back to it and redo it. I drew one line because it happened to work in that scenario. But it really should have been 3 separate lines. This one, and then one that's almost the same, and then one that's almost the same. Right? So it should have been 3 different lines, but one line kind of hit them all, so I just drew it that way. But okay, so let's look at, I'm actually going to run this one in SAS. There's another example. Gosh, this is frustrating. Now I was able to go too fast. So, I don't know what NKNW means, but something northwest. But this is cases of crackers sold. I thought death from cancer might be a little too heavy for you guys, so we'll do this. This is selling crackers in a store, right? So why is the number of cases of crackers sold during the promotion period? So this is a study of ad campaigns. What's the best way to advertise our crackers, right? So you have 3 types of promotions. Customers sample the crackers in the store. You ever walk around Sam's Club? Right? And there's like 15 of those booths set up and they want you to try. That's one way to promote your thing. You go into stores and then additional shelf space. You can promote it by putting more of them out there. Right? That's the one that is most there, so they're going to grab it. Or you can make special display of shelves. So those are the ones that sit out in front, and usually around the Super Bowl they make them out of beer cartons and stuff. Out, buy our beer. Right? So 3 different types of promotions. And then they keep track of how many cases are then sold during that promotion period. If you analyze the data, this is SAS code, you don't need to worry about that, but here's the actual data. So number of cases sold is your Y variable, and then the number of cases sold in the last equivalent period, and then which treatment they got. Now they use the word treatment generically. It should say factor, or it should say promotional type, right? So I probably would use the word type. And then what store it is, we're not going to do anything with the store, but sometimes, you might adjust for what store it is, because some stores sell more than other stores no matter what kind of promotion you have. Kind of depends on where that store is located. A store in the middle of Topeka might sell a lot more crackers than a store up in Holton. Right? So if you plot the data, it's hard to see these. I can see them, but from where you're at, you probably can't see them. But that's 1, 1, 1, 1. There's a 1. That's a 2. 3, 3, 3, 3. 2, 2, 2, 3. So they're intermingled, but it does seem like the 1s are more to that side and the 3s are more to this side. So they've intentionally imposed this imbalance again. But so let's go to SAS now and analyze this data. So again, this is SAS code, and you don't need to know what it's doing, but this is PROC GLM, which stands for General Linear Models. So when you click, if you ever get to go back into Enterprise, you click on Tasks, and then ANCOVA, and then Linear Model. That's the PROC it's using. Right? General Linear Models. So I can put in there, class variable is type. The model is the Y variable cases equal type. And then I'm asking for means comparisons and all that. So if I run that, it's really not a very big data set. Okay. So you get a lot of stuff that we're going to look at, but there is the ANCOVA table. So you get 2 degrees of freedom for type, because there were 3 types, and there were a total of 15 observations. Right? I think it was evenly divided, 5 per group. And we get a p-value of 0.016. The type 3 sum of squares down at the bottom, this is all variables in the model if it was more than 1. Here it's just 1, so that's going to match. 169.4, 169.4. Same p-value. What's the conclusion? There is a significant difference between types. So well, when I use this thing, it moves awful fast. I want to get back to there. All right, so here's a graphical depiction of the comparison of the means. The means are the diamonds in the middle of each box plot. So we see that type 1, type 2, they're not real different. But type 3 is a lot different. Type 3 was special displays, right? So that's the one that looks to be different. So if we do the LS means, you remember, have I talked about LS means? LS stands for least squares. So these are called least squares means, right? And it's called that from the least squares regression. So these are adjusted means using the regression variable. Well, it uses that term whether you got a covariate in there or not. So LS means these will equal the raw means that you would get if you just computed them yourself from the 5 stores if there's nothing being adjusted for and if everything is no missing values. So you got 38.2, 36, 27.2. This little matrix is a matrix of p-values. I asked for the means comparisons. What is this 1.00? That's a p-value, right? It says PR greater than absolute value of t. So you have to learn to read output. That's probability of being greater than the test statistic t. It has absolute values because it's a two-tailed test, right? So it's p-value. What does a p-value of 1 tell you?
100%.
That's 100%.
It means, yeah, that there's absolutely no difference between them. Now, it isn't really going to be 1, but the 4 decimal places, it's 1. So it's probably 0.999999 something, something, something. Right? And then we have 3. Under the 3 is a 0.0148. But this is a matrix, so it's group 1 versus group 3 has that p-value. Right? So that's 38.2 compared to 27.2. Significant difference. 2 versus 3. What's the conclusion?
And they're still pretty different.
They're pretty different. It's not significant at the 0.05 level, but darn close. Now I asked for adjustment for multiple comparisons, the Bonferroni method. So this is what's called an adjusted p-value. Rather than me have to take, 0.05 and I need to divide by 3 because I'm doing 3 comparisons, it takes the raw p-value, the unadjusted p-value, and multiplies it by 3 to get a p-value you can just compare to 0.05. Right? So the real p-value would have been a third of that. Real, that's not the word I want. The p-value before adjustment would have been a third of that. Then it multiplied by 3 because we did 3 comparisons. So not significant using Bonferroni. Okay, that's very uninteresting. But now let's take a look at the covariate. So first thing I want to do is some plots. Actually, let me run both of these. The plot above this is exactly the same plot, but without the lines drawn in it. So that's the plot they were showing a minute ago, but it's a little easier to read. You see the 1s over here, you see mostly 3s over here, but there is a 3 way down here, and so on. Now, if I fit a separate line to each group, that's what those lines would be. So analysis of covariance moves the mean of that group along the line till it hits the overall vertical line for the overall mean for the number of cases sold in the last period. The analysis of covariance assumes equal slopes. These look pretty equal, not exactly equal. They're never going to be exactly equal, but in the model, when you fit the model, it will, it will use the same slope. So then to fit that, I just add the last variable, the variable called last, into the GLM model and run that. And I get to the ANCOVA table. One more. Well, actually, let's just do the means comparison, since I'm out of time. Now look at the comparisons. What do you notice?
They're all significant.
They're all significant. So I gained power to test those means by adjusting. So the means actually got further apart, the error got less, so the means comparisons become significant. All right, sorry, I ran long. I'll let you go. But enjoy analysis covariance. I'll have this posted out there, and I will have a homework assignment based on it out there for you.
When's that due?
It'll be due